Hello, everyone, and welcome to our Fellows Public Talk presentations. I'm Claudia Rizzini, Executive Director of the Fellowship Program at the Harvard Radcliffe Institute. It is my pleasure to introduce Aaron Meisner, our Carl and Lily Pforzheimer Foundation Fellow. At the heart of space research lies a fundamental curiosity about big questions. How did it all begin? Why are we here? And are we the only ones? Despite centuries of searching, astronomers still may not have found all of the Sun's closest neighbors and don't know for certain how many planets inhabit our own solar system. Aaron started his work as a space cartographer. He combed through hundreds of trillions of pixels in images captured by the WISE telescope that chart the entire night sky and to track how its conditions changed over time. At that time, astronomers were observing strange movements in the solar system's outer reaches that were thought to be indicators of a new planet hundreds of times farther from the Sun than Earth, called Planet 9. Aaron searched his skies map to check for traces of Planet 9. While he did not find it in his maps, Aaron suspected that the planet and other cold worlds could be hidden in the ocean of data generated by NASA telescopes. Instead of relying solely on supercomputers, Aaron co-founded the Backyard World Project, which calls on the public to sift through images of the sky that confound algorithmic searches. With the other 200,000 participants around the world, the Backyard World Project acts as a search party for both Planet 9 and brown dwarfs that inform discussions about star and planet formation. While at Radcliffe, Aaron is undertaking a renewed hunt using freshly captured images of the southern sky viewable from Chile. With the help of image processing, machine learning, and the Backyard World participants, Aaron hopes to reveal celestial objects lurking in the Sun's local neighborhood and outer solar system, more broadly exploring the ways human and AI can collaborate on astronomical discoveries. The Q&A portion of the public talk today will be moderated by Radcliffe Fellow Nidia Menon, Professor of Economics at Brandeis University. And now please join me in welcoming Aaron Meisner.
All right, thank you, Claudia, for the great introduction. And thank you to the entire Harvard Radcliffe Institute staff for everything they've done all this year to make it such an awesome fellowship year for our cohort of Radcliffe Fellows. Today I'll be telling you about my work crowdsourcing the hunt for nearby worlds over the past decade or so. So in astronomy, one of the most timeless quests that's gone on for centuries now is to search for new undiscovered planets in our own solar system. But did you know that Neptune, which was discovered in 1846, more than 150 years ago, is the only planet in the solar system that's ever been found by a correct mathematical prediction? By contrast, Pluto, for example, was a chance discovery made in 1930 based actually on a faulty prediction of a new distant planet in the outer solar system. And by the way, we also know now that Pluto is considered a dwarf planet rather than a planet as of 2006. Nevertheless, there are still relatively modern theories of additional as yet undiscovered planets in the outer parts of our own solar system. The main one in this category is what's referred to as Planet 9. So you can think of this hypothesized Planet 9 as like a super-Earth, so a rocky world similar to the Earth, but say 5 times more massive, 5 times bigger, and about 20 times further away than Neptune. So as Claudia alluded to, 20 times further away than Neptune would put you way out in the far parts of the solar system, hundreds of times further away from the sun than is the Earth. This photo here shows the team of 2 Caltech astronomers who first proposed this Planet 9 in 2016, including in the center is Mike Brown, who goes by the handle of Pluto Killer on various social media because he likes to take credit, at least in part, for the demotion of Pluto from planet to dwarf planet several years ago. And so wouldn't it be ironic if he then went on to propose a new sort of replacement version of Planet 9 that Pluto used to be? There's another one that I refer to here as Planet X. This has essentially been ruled out, but only within the past 10 years or so. And this you can think of as like Jupiter, but about 5,000 times further away, so maybe 20,000 times further from the sun than is the Earth. And the key thing to keep in mind here is that it still is possible to propose new planets in the solar system. They just have to be in the outer parts of the solar system where it's cold and where they're small enough and faint enough that they could have eluded detection for all of these centuries of searching. So when we think about the continuum in terms of sizes of astronomical objects and temperatures of astronomical objects, there may be more of a continuum between stars and planets than folks realize. So on the right here, we have the sun is representative of a normal star, a so-called main sequence star, where the main sequence means that it is bright because it's fusing hydrogen in its core. But you can go to fainter, colder stars than that, and so-called red dwarf or M-dwarf stars, and these are actually the most numerous stellar inhabitants of our Milky Way galaxy. They can be up to a factor of about 2 colder than the sun. And then all the way at the other end of the spectrum, you have Jupiter, which is a factor of several dozen times colder than the sun, about 150 Kelvin in the units we like to use in astronomy. But in between the coldest red dwarf stars and the biggest Jupiter-like giant planets, you have what are called brown dwarfs. And these are a mysterious and probably lesser known type of celestial object, but they fully bridge the gap between the smallest red dwarf stars and the largest planets in terms of both mass and their temperature. So for example, what we would refer to as a very cold brown dwarf, shown here, 300 to 500 Kelvin, is more than 10 times colder than the sun, but nevertheless, this is a case where one needs to orient themselves to the scales of, say, cold or nearby in astronomical terms relative to what we think of in everyday human life. So 300 Kelvin would be a very cold brown dwarf, but that's about 80 degrees Fahrenheit, so a little bit hotter outside than it is outside today, right? And a 500 Kelvin brown dwarf, still very cold, 10 times colder than the sun. That's about the temperature that you would heat your oven up to in order to make frozen pizza, basically. And so one thing to keep in mind here when we think about cold versus hot in terms of astronomy is the wavelengths of light at which these things can be detected. So stars, because they're so warm, they can be readily detected at the visible light wavelengths that the human eye uses, or that traditional photography has used, or that telescopes for centuries have used. But for brown dwarfs, or things that are the size of planets, they're so small that they emit mostly in the infrared, similar to the human body. The light we see coming off each other is reflections, whereas we would need an infrared camera to actually see the heat being emitted by something the temperature of the human body. And so it's really only recently that we've had the infrared technology to be able to discover these very cold brown dwarfs. And thankfully, within the past 15 years or so, there's this NASA WISE satellite, which has provided a revolutionary new view of the infrared universe. WISE stands for Wide Field Infrared Survey Explorer. It was launched in late 2009. It observed for most of the 2010 to 2024 time period before it actually re-entered Earth's atmosphere and burned up in summer of 2024. But before that, it was in low Earth orbit around the sun. It was constantly riding along the dividing line between day and night, pointing directly outward from the Earth. So there was no notion of day or night, really. It was just constantly looking straight outward, 24/7, 365, taking 2 images of the sky, about a megapixel each, every 10 seconds. And as the Earth goes around the sun, you sweep out these circles across the sky, and gradually, as the Earth orbits the sun, these circles progress to the point where every 6 months you get a full sky mapping. And so over the course of 15 years, WISE obtained something like 25 full sky mappings in more sensitive data and deeper data than we've ever had before. So it really left a strong legacy of mapping the infrared universe. And one of those legacies that WISE really left in terms of the infrared universe is specifically in what we call the solar neighborhood, the very immediate nearest stars and brown dwarfs closest to the sun that we know of. So this is a diagram of what we call the solar neighborhood, the closest known star systems and brown dwarf systems to the sun. Again, when we talk about nearby in astronomy, several light years means very nearby, even though, of course, light years is almost an unfathomably huge distance for a human relative to what we see in everyday life. So what you may notice here are objects like Barnard's star, Alpha Centauri, Proxima Centauri. These are relatively famous household names in astronomy. They've all been known for more than a century. They are the first and second closest known systems to the sun. And the reason they've been known for more than a century is because they're stars, they're bright, we can see them in visible light. And then it was sort of a 100-year gap, and then all of a sudden, as soon as WISE came online, we found two new systems, WISE 0855, shown here, and WISE 1049, aka Lumen 16AB, which are now known to be the third and fourth closest systems to the sun that we know of yet. And so these were really historic discoveries that were made only within the past 10 years or so, after sort of a century of finding nothing, thanks to this new infrared view of the universe. So how do we go about actually making these discoveries of nearby celestial objects, well, whether that is planets in the outer solar system, or nearby brown dwarfs, or nearby stars? And the answer is celestial apparent motions. The way this works is that everything in the universe is actually moving relative to one another. Everything is moving relative to our solar system. The trick is that the relatively nearby things, we can see those motions in a perceptible way on, say, 1 year or 10-year timescales that humans can monitor, as compared to the very distant stars and galaxies, say tens of billions of light years away, which they are moving, we just can't perceive it over human timescales. You can think of this as an example in human terms of if you were to hold an object at arm's length and move it side to side by 6 inches or so, you would visibly perceive that side-to-side motion. But if you were to take that same object and put it a football field away, say 100 yards away, and move it that same 6 inches, you may still be able to see the object, but you won't be able to perceive its motion just with your eye. So indeed, this is somewhat of an old-fashioned astronomy technique, but it's still used to this day to look for moving objects as a way to discover planets and our nearest neighbors. So Barnard's star, which I showed in the previous diagram, its motion was discovered, and hence its nearness was discovered in 1916, more than 100 years ago, and it remains the fastest known apparent motion of any brown dwarf or star. This movie shows an example of that, where it's kind of like a time lapse over 20 years or so. You can see there's some dots in the background. Those are just normal, more distant stars and galaxies that are far away. We can't perceive their motion, except for Barnard's star, which is in the foreground, moving quickly downward in a linear fashion. This also is exactly how Pluto was discovered famously by Clyde Tombaugh at Lowell Observatory in 1930. He had acquired images all over the sky and had meticulously been comparing them one to the other to look for anything that would move and search for a hypothesized planet in the outer solar system. And in hindsight, we have the benefit of this arrow that's shown here pointing to where Pluto was in January 23, and then 6 days later on January 29th. Of course, this was much, much harder when you didn't know what you were looking for. And so there's a technique that astronomers have liked to use historically and still use to this day, which we refer to as image blinking. And the idea is that if you align two images of the sky as best possible so that the normal stars and distant galaxies look the same in the two images, then for whatever reason, the human pattern recognition is much better at more easily perceiving what's changed, whether that be stars that have changed in brightness or a star that has moved, a planet that has moved, an asteroid that has moved. Historically, astronomers actually used a mechanical device for this. It was called a blink comparator device, and so it's a custom piece of hardware that an astronomer could use to toggle mechanically between two pictures of the sky. Nowadays, we have digital cameras and computers, so we don't need a blink comparator device. We can do that by uploading our digital images of the sky to a computer and using software to blink between them. And so I think this presents a great opportunity to really crowdsource the astronomical discovery process of moving objects or objects that change over time on the internet by involving tens of thousands or hundreds of thousands of volunteers. Shown at bottom is the Zooniverse, which is one online crowdsourcing platform which allows you to do this in a massive scale way. And we also have reason to think that this should be a productive thing to do because amateur astronomy has a long history of making major contributions to cutting-edge astronomical research. One discovery that embodies this is comet Hale-Bopp, which was discovered in the 90s, one of the brightest comets of the 20th century. It was co-discovered by Thomas Bopp, who was an amateur astronomer in the Phoenix area of Arizona. So in addition to just being an efficient way of mining a lot of astronomical data in a way that has many hands making a light load, this crowdsourcing is not only good at getting through a lot of data in a short amount of time, but it's also really good at discovering the sort of unknown unknowns So I'm going to show a couple examples here of these online crowdsourcing Zooniverse astronomical discoveries that have been made where they were totally unexpected, unknown phenomena that were revealed by the volunteers. One of these is called Hanny's Voorwerp, where I believe Voorwerp is Dutch for object or thing. It was discovered in 2007 by the Zooniverse Galaxy Zoo project, specifically by Hanny van Arkel, who's a Dutch school teacher. The Hanny's Voorwerp is the odd-looking green thing shown in this image, which is now understood to be a case where the galaxy more near the top of the image has a supermassive black hole in its center that's shining radiation into intergalactic space and is illuminating a cloud of material in intergalactic space, making it glow green. Another relatively well-known example of a discovery made through participatory science, through online crowdsourcing, is so-called Tabby Star, which was discovered in 2016 by the Zooniverse Planet Hunters project. And what you can see here is that the star has what we call a light curve, the brightness as a function of time, that displays very weird dips, up to 20% dimming in its light. But the dips aren't totally regular, they aren't totally periodic, they don't have a reproducible shape, which is all very strange relative to other previously known astrophysical phenomena. And so what got folks really excited about this, especially the astronomers who work in the subfield called Search for Extraterrestrial Intelligence, or SETI, is the fact that this looks kind of exactly like what you would expect from a Dyson sphere type of scenario if you had a technologically advanced alien civilization around another star that was harvesting the light from that star. Now it turns out that there are ways to perfectly well explain this object using normal astrophysical dust orbiting the star rather than alien megastructures. But nevertheless, this is a great example of finding something previously unknown through this participatory science project. So in 2017, we thought, wouldn't it be great if we could do this same type of online crowdsourcing of massive amounts of astronomical data, but for the project of finding new planets in the outer solar system, or finding new nearby neighbors to the sun. And so that's what we call Backyard Worlds. Backyard Worlds Planet 9 is the full name. And this is a little bit of a promo video that we have for it, showing sort of a tour of the solar system and into nearby interstellar space. So indeed, we now learn that there are 8 planets in the solar system, not 9, ever since Pluto was demoted. We're now zooming out from the inner solar system. We're passing relatively well-known planets here: Jupiter, Saturn, Uranus, Neptune. We now call Pluto the king of the Kuiper Belt, so we don't consider Pluto to be a planet by our current definition, but it's in this area of the solar system, about 35 times further from the sun than is the Earth, called the Kuiper Belt. As of 2016, astronomers do predict there's a new 9th planet called Planet 9 in the outer part of the solar system. That's where we're zoomed out to at this point. Critically, even though we think there may be hints that this planet exists, we don't know its exact position or mass or size. So that's why a data set like WISE can be so valuable for this search, because we need to search the entire sky, these entire hundreds of trillions of pixels, to maybe find one object, or maybe not. Now we're going to zoom out into the closest regions of interstellar space to the sun, the so-called solar neighborhood that I was talking about earlier. Only recently, within the past 30 years or so, thanks to this infrared technology I mentioned, have astronomers discovered the first examples of brown dwarfs. So brown dwarfs, because they're not massive enough to fuse hydrogen like the sun does, they are faint and they only emit in the infrared, or much more so in the infrared, and so they can have remained hidden for centuries and only be discovered now. And 2 of the closest systems to the sun, the 3rd and 4th closest, are now known to be these 2 brown dwarfs discovered using WISE data, WISE 0855 and Lumen 16AB. WISE 0855, by the way, is 250 Kelvin, which is 100 degrees hotter than Jupiter and is about the temperature of the North Pole. So this is an example of the data we upload to Zooniverse, showing how WISE 0855 is moving side to side over the course of about 10 years. So fast forwarding a bit from 2017 to when we launched the project to now, how have we done? What are some of the outcomes that we've had from this project? Backyard Worlds has been successful along various axes, I would argue, including both public engagement as well as just the raw scientific discoveries. So by now, we've obtained over 9.5 million classifications from Backyard Worlds volunteers, where a classification means one volunteer looking at one patch of the sky as it changes over time in the WISE data. And if you think about it, this is equivalent to scouring the entire sky about 9 times over with this data set. We have more than 90,000 registered users. We believe we have about 200,000 unique volunteer contributors. That's because you actually don't even need to register to contribute. Participants come from all 50 US states, plus Puerto Rico and DC, and 167 countries worldwide. So who are the Backyard Worlds volunteers? One thing that I think has been great about Backyard Worlds is the great diversity of our volunteers across a lot of different axes. So one shown here is just the geography. Folks who participate in this project come from all over the world. They also come from all different backgrounds in terms of what formal training, if any, they have, or what they do in their day job, day-to-day, outside of being an astronomy enthusiast and participating in research online. So for example, there are many folks here representing the USA, but also other countries, including France, Scotland, and Argentina. Now showing the breadth of what these folks do in their day-to-day lives. This also has a wide range from lawyer to high school student to retired bioscientist to stay-at-home mom and so forth. And I think this has really benefited our project tremendously because there's a concept of expert bias where if you only have a really small group of professional astronomers looking at a huge amount of data, you're likely to get yourself in a somewhat of a rut of people are just regurgitating the same database queries that they ran and learned from their thesis advisor, maybe with a few variations or with a new data set. But when you bring in someone, say, who's trained as a data scientist, all of a sudden you have a totally new way of looking at the data. And this has really shown tangible benefits to us as far as what we've been able to discover. One other thing we've learned through Backyard Worlds is that the community building aspect really matters. You can't just dump a bunch of data onto the internet and wait for people to click on it and call that a participatory science project. It makes a big difference and it helps a lot to really get to know the volunteers. This can provide two-way feedback both from you to the volunteers as well as from them to you. And so one example of this is that we always invite our volunteers to join our weekly science team hangouts. So every week, every Thursday, we have a Zoom call where we have our small team of professional scientists and we invite several hundred of the volunteers who we call advanced participants or super users who have given us their email addresses. And instead of having this be a closed door meeting where we discuss what science we're going to do, what papers we're going to write, what telescope time we're going to ask for, we have also the volunteers involved at every stage in this process. So here what's shown is, I think, a fun example of a scenario we encountered on one of these calls where everyone got a kick out of it. We all realized that David, who was on the call, was calling in from his high school lunch period at the library. And I thought that was awesome because I don't know what I was doing during lunch period of high school, but it was definitely not talking about astrophysics research with professional NASA scientists. Now just to put some images to the words here, Backyard Worlds has discovered something like 5,000 brown dwarfs over the course of the past 9 years. And these images, I think, really tie together this idea of discovering nearby cold objects through their motion. So this is an example set of 6 of our discoveries out of many thousand that I'm showing here. In each case, you see one orange object that's moving subtly near the center of the frame, as compared to many, many other objects that are in the background. They just look like black dots. Those are much more distant stars and galaxies. And so all of these are now known to be very cold nearby brown dwarfs, first discovered by our Backyard Worlds volunteers. The deep orange color is also a big tip-off that these are cold brown dwarfs as opposed to warmer stars, because these objects are emitting much more at the longer infrared wavelengths, which is how these images are color-coded to make them orange. Another set of discoveries that's been super productive from Backyard Worlds is what we call cold companions. And the idea here is that in each of these 5 image blinks, you see, again, one orange object near the center that's moving as compared to the stationary background black stars and galaxies. But you also see in each image another much brighter, larger, more massive star that is moving with the same rate of speed and in the same direction as the orange-brown dwarf. And so the fact that these objects are co-located on the sky as well as moving with the same direction and same speed, that tells us that they must be physically associated in what we call wide binary pairs. And so what I think is awesome about this is that it's sort of like we're witnessing the Planet X scenario play out in other stars in our local cosmic neighborhood of the Milky Way. So even though we haven't found Planet X in our own solar system and are dubious now that it exists, we've still found examples of the same type of Jupiter at tens of thousands of astronomical units in other nearby star systems. Here's a 3D rendering of a subset of our 5,000 brown dwarfs discovered through backyard worlds. We know where these objects are on the sky because that's how we find them, but then we also know how they move. That's how we discover them in the first place. So one thing that's amazing is that we can actually fast forward, speed up many millions of years, many millions of times, and see how these objects that happen to be nearby to the sun at the center of these green circles here will eventually disperse over millions of years throughout the Milky Way galaxy, even though they all happen to be very nearby to us at the present day. And so if you think about it, Backyard Worlds has discovered about 1.5 brown dwarfs on average per day since it was launched, which I think is really cool. Here's another 3D animation showing some of our Backyard Worlds discoveries, but this time trying to give a bigger sense of perspective of what nearby means. So we started out thousands of light years above the Milky Way plane in this visualization, and then we zoomed in. You'll note that the sun is actually not at the center of the Milky Way, right? It's several tens of thousands of light years away from the center. And we have to zoom way, way in until we start seeing these orange dots here, which are nearby stars to the sun. The sun is at the center of this blue-green grid. And then only when we continue zooming in even further do we start to get to the white dots, which are the Backyard Worlds discoveries rendered in 3D here. The Backyard Worlds discoveries, they aren't just curiosities, but they're really pushing forward our knowledge of the universe, our knowledge of astrophysics, and this is attested to by the fact that we have a major ongoing Backyard Worlds follow-up campaign, where follow-up in astronomy means just gathering very detailed, specific information on an object that you've identified from a bigger survey data set like WISE. So we've used every telescope, essentially, all the premier telescopes on Earth and in space to follow up these discoveries made by members of the general public through Backyard Worlds. This includes both Gemini 8-meter telescopes in Chile and Hawaii, the Mayall telescope, the Blanco telescope in Chile, also Hubble Space Telescope and Spitzer Space Telescope. These are two of NASA's great observatories. And most recently, we've also been able to obtain very precious telescope time on the James Webb Space Telescope, which is sort of like a Hubble successor, in order to follow up discoveries specifically made by Backyard Worlds volunteers. And so I think our follow-up process also embodies our idea of maintaining engagement with the volunteers throughout the entire scientific process. When we submit these requests or so-called proposals to ask for telescope time on these premier resources like Hubble or James Webb Space Telescope, we often include as co-investigators the volunteer discoverers of the objects that we're aiming to observe. So I think this was summarized nicely in this one social media post by Guillaume here, who is a pulmonologist in France who's been involved with Backyard Worlds for many years. He said, one sentence to summarize the awesomeness of Backyard Worlds: I, as an amateur, have been able at some point in my life to influence the motion of Hubble. What a great feeling. So similar to this idea of Hani's Voorwerp and Tabby's star, we've also seen serendipity come up in a big way in the Backyard Worlds project, and indeed sometimes the best discoveries happen by accident. Here's a clear case of that in Backyard Worlds. This is a brown dwarf that's actually been nicknamed the accident by its discoverer, Dan Castleton, who's a participatory scientist who actually lives in the Boston area. The image blink shown here is showing the true WISE discovery images of this unusual brown dwarf. So Dan was really into this project. He was running his own image processing pipeline, his own machine learning pipeline on all the WISE data to try to find new brown dwarf discoveries, and his pipeline had told him that there was something new right in the center of this image, but right at the center of this image there actually really is nothing there. There's just noise or maybe just blank background. But if you look down towards the corner, you can see this very, very faint brown-orange dot moving diagonally downward, and that is what we refer to as the accident. You may even think that it's so faint and so unconvincing that it's just pixel noise in the data, and that would have been a reasonable way to look at it until we eventually did get James Webb Space Telescope, Hubble Space Telescope, Spitzer Space Telescope, and Keck data all on this object detecting it. And so we now know that this is real, and we also know that it is a very unique celestial object unlike any other planet or brown dwarf that we know about. It's a so-called halo brown dwarf, meaning it's in the halo of the Milky Way, which is an ancient population of stars in the Milky Way. It has a very primordial atmosphere that's nearly free of metals. Most brown dwarfs, they actually have a lot of detectable water and methane, for example, but the accident has much less. Not only have there been a few really key revealing discoveries like the accident from backyard rules, but just the fact that we've discovered so many more of these brown dwarfs has led to big changes in our understanding of astronomy and the Milky Way. So in a sense, we've revised the Astro 101 type of knowledge on brown dwarfs in that for many years, the local Milky Way ratio of stars to brown dwarfs was thought to be 6 stars for every 1 brown dwarf. But recent discoveries, especially from backyard worlds, have actually increased the estimated prevalence of brown dwarfs to be 1 brown dwarf per 4 main sequence stars. So that's a big factor increase in how much of the population of our own Milky Way galaxy we now think is made up by these brown dwarfs rather than just stars. I think a reasonable question to ask at this point, given where we are in society and technology, is what about artificial intelligence? I've sort of touted crowdsourcing as a way to process a lot of data, but surely artificial intelligence or machine learning, however you want to refer to it, is also an alternative here. And so one example of this where we've tried to unite forces between the machine learning, the artificial intelligence, and the human element, the crowdsourcing, is a project I launched in 2023, a spin-off of Backyard Worlds called Backyard Worlds Cool Neighbors. And the idea is that we use machine learning pre-selection to specifically single out patches of sky that we think are most likely to harbor nearby undiscovered brown dwarfs, whereas with the original Backyard Worlds Planet 9, we were just showing random large sky patches in order to cover the sky in the most efficient way possible. And so we can think of this as trying to use the AI in a benign way, right? Because we want to make sure that volunteers' time is being used as efficiently and appropriately as possible. So wouldn't it be best to show them regions of the sky that we think are the most likely to have the discoveries we're interested in? And so this small orange rectangle here shows you how much you can narrow the field of view for Cool Neighbors as compared to the much bigger field of view shown for Backyard Worlds Planet 9, also in comparison to the size of the full moon. So previously we were showing patches that were a substantial fraction of the size of the full moon. Now we can really narrow it down, and we were able to measure the effects of this because of the fact that we have the original version of the project as well as this sort of machine learning enhanced version of the project. And we find that there's a 2 to 5 times boost in classifications per participant. So in a sense, you could think of this as being better retention of the volunteers. They stay around longer to make more classifications each, thanks to the fact that we're giving them a more focused, higher priority view of the sky each time they look at something. And we also get a 3 times boost in classifications per unit time. So folks are able to run through these image blinks, these subjects, to do their classifications more quickly and more efficiently, we think, thanks to the combination with machine learning now. So in my last few slides, I wanted to transition to talk about sort of the next big thing in astronomical big data in this new era of data-intensive astronomy. And that is something called Vera C. Rubin Observatory. When I'm not at Radcliffe, this is a project that I had been working on for several years now. So Rubin Observatory will perform the Legacy Survey of Space and Time, LSST, from 2026 to 2036. It's going to start literally any month now, so it's a very exciting time for Rubin Observatory and astronomy overall. Rubin Observatory has amazing state-of-the-art cameras, so each image from this camera will get more than 3 billion pixels. You can see in this diagram here that the camera itself is larger than a human. Rubin Observatory will cover the entire southern sky visible from Chile every 3 nights, and the reason it can do that so quickly and so efficiently is because it has a huge field of view. As you can see in one of these images that's rotating through here, the field of view is more than 40 times the size of the full moon in terms of area. Over the course of its 10-year time period with the LSST, Rubin Observatory will obtain roughly 1,000 images of every part of the southern sky. So it'll be, in a sense, the biggest ever color movie of the sky. Rubin Observatory will detect 17 billion stars and 20 billion galaxies in total, and this is neat because this will be the first time that astronomers have ever detected more stars than there are humans on Earth. Just to show how massive of an undertaking this really is, here's a time lapse of the Rubin Observatory construction over the course of about 10 years or so. And as I mentioned, the camera is the height of a human, basically 6 feet or so. But then everything else surrounding the camera is enormously huger than that. So the primary mirror, for example, which gathers all the light, which then gets detected by the camera, that primary mirror is 8+ meters in diameter. So that's quite huge. And then it also goes on a huge telescope mount, which allows the telescope to slew from one sky position to the other very rapidly in the course of a night to take on the order of 1,000 images every night. Then the mount itself is enclosed in this massive dome, and the dome can rotate around. The dome is there so that the dome can be closed to keep everything protected during the day or during bad weather, but then it can open up at night so that you can look out to the sky. And you can see here in some of these images, like a truck, for example, or a human, for example, is just so tiny in scale compared to all of this. One of the most important scientific areas of Rubin Observatory is going to be the solar system. It's one that I'm most excited about. And the reason is as follows. There's currently about 1.5 million asteroids that are known in our solar system, which have been discovered gradually over the course of the past couple centuries. But Rubin by itself, over the next 10 years, will discover another roughly 5 million asteroids. So it'll make a huge factor increase in the total number of minor bodies that we know of in our solar system, and this will revolutionize our view of the solar system. It's interesting and fun to note here that Rubin Observatory, the way it's going to discover all these asteroids is exactly what we've been talking about this whole time, the fact that they move across the sky in a way that's perceptible and detectable relative to background stars and galaxies, as been showing here. You can see this asteroid start to move. And indeed, in only its first few nights, every night Rubin Observatory was discovering 1,000 to 2,000 asteroids. So Rubin really is our next great hope for detecting Planet 9 if it exists. Of course, there's a caveat here, which is that what if Planet 9 is in the northern sky rather than the southern sky, in which case maybe it could remain mysterious and unknown beyond even LSST and Rubin Observatory. But regardless of whether Rubin discovers Planet 9 itself, it will undoubtedly discover large numbers of extreme objects in the outer solar system. One last note on Rubin Observatory is that I think they've done a really smart job of integrating this idea of crowdsourced participatory science into their plans from the beginning, rather than having it being an afterthought or be a small part of what they do. So I think in a sort of brilliant move, they've partnered directly with the Zooniverse to send Rubin Observatory data directly to the Zooniverse crowdsourcing platform in order to make it easy for large numbers of different teams of astronomers, maybe even hundreds of different teams of astronomers, to all launch their own participatory science projects online with the Zooniverse. And so I will surely be interested in participating in this. In fact, with my Radcliffe research partner, Hannah Burrows, this year, who's a senior at Harvard College, we've built a prototype of Backyard World's Rubin, where we are blinking images of Rubin and prior telescope data to do exactly this task of looking for moving objects. So Rubin really is a huge data mining opportunity. It has something like 10 quadrillion pixels that it will gather of single exposure data over its 10 years, and 7 trillion single exposure detections of celestial sources like stars and galaxies. So it's a huge opportunity, but also a huge challenge if you're looking for, say, one rare object, one planet among all of that. And I think that AI, supercomputers, and participatory science will all help realize Rubin's full discovery potential in this context. So to conclude, I want to leave one last slide here. The art here was actually made by one of our Backyard Worlds volunteers who likes both science and creating art. He made this originally for a NASA press release that we did on our Backyard Worlds discoveries. So I'll leave with a couple of statements and a few questions, which maybe we can touch on a bit more in the discussion afterwards. So in conclusion, participatory science has a storied history of revealing unanticipated but scientifically important discoveries and breakthroughs. Examples of this from astronomy include things I mentioned like Hanny's Vorwerp, Tabby's star, and the accident from Backyard Worlds. Big data and artificial intelligence are becoming increasingly prevalent across scientific disciplines. Astronomy, I think, has been at the forefront of this just because of the fact that you can go to a telescope, take one image, and have billions of pixels of data. But this is a trend that's happening more broadly across science, including, say, like earth science and climate science. So questions that come to my mind that I think about sort of on a day-to-day basis when I'm running these participatory science projects or thinking of launching a new one, and maybe questions that we can get some insight to from looking at what's worked and what hasn't worked in the past with Backyard Worlds, are as follows. How do we preserve the human element of scientific discovery going forward, assuming that we do want to preserve it, and I think we do, but perhaps that's a question. How can participatory science be used to enhance the public's trust of science? And how can we scale participatory science to meet the challenge of ever more enormous data sets like that from Rubin Observatory? So I'll end there, and thank you.
Aaron, that was amazing presentation. To quote from our own David Kring, sitting right up in the front, I think we are starstruck, perhaps even twice in this. So let me start by sort of noting that data tells us, if we track New Year resolutions in sort of Western cultures that think of time in a linear fashion, the most likely things are likely to be things like, lose weight, exercise more, that is lose weight, eat healthier, lose weight. And so I think we see a pattern here. But on top of the list are also things that reflect our fascination with the stars in the universe, right? So things like learn the night sky, so the constellations, learn astrophysics, become an astronomer, build a telescope to observe the planets, start astrophotography with shots of the galaxy or the Milky Way. And depending on where you are in your life cycle, become an astronaut. Okay, so I gave up on that dream about 30 years ago at this point. So all of this I've sort of rationalized in my head as sort of revealing what visionaries like Carl Sagan have said, which is that the cosmos is within us, right? And we are all sort of made of stars stuff, living on this pale blue dot in this vast expanse of space. So as someone who's at the forefront and the cutting edge of research in this area, I'd like to begin by asking, of all the things that you could have focused on when you started your career, why did you focus on this specific area of research, which is this hunt for brown dwarfs?
Yeah, it's a really interesting question, especially because I feel like there's kind of a cohort of astronomers, maybe like half of astronomers, who will say, oh, I looked at the stars from my backyard my entire life, and I always knew I wanted to be an astronomer, but I definitely was not like that. I didn't know anything about astronomy till college, basically. It really wasn't on my radar. I grew up in the Seattle area, which is not really a hotbed for astronomy, just based on the climate, for example. You'll be lucky to see the sun sometimes there. So to me, it was really the combination that astronomy brought of data and math and physics and science and coding all rolled into one. So when I went to college, I sort of had a sense I wanted to be maybe like a physics or computer science major, but I didn't know anything more specific than that. And one of my statistical mechanics professors was an astronomer, and I just kind of liked his style. He had a very no-nonsense style of doing research, which maybe sounds ironic compared to being an astronomer, but nevertheless, I chose it based on the professor, and I just found that I really liked it. I had done previously research like in a physics lab where you'll work for 6 months or a year to get one data point in an Excel spreadsheet, but the projects we were doing in the summer research project, we had many, many images we would take in one night, each with millions of pixels. And so to me, what drew me actually was really just the data-driven science aspect of it. And then more specifically regarding, brown dwarfs, Planet 9, I think I just really like the idea of this cosmic treasure hunt or the celestial rare object search, the idea that you could have tens of trillions of pixels of data and be looking for one thing in that. Like, I like the challenge there of it sounds impossible, but maybe you can do it if you combine the right sets of techniques. I also, similar to some of the questions that Claudia raised earlier, I like this question of what's out there. We know enough about the universe to kind of be intrigued, but there's still so much we don't know. So for example, we now know of thousands of exoplanets in our own Milky Way galaxy, where an exoplanet is a star or a planet around another star other than the sun. And yet we still don't know how many planets there are in our own solar system for sure. And so the idea of joining this kind of like centuries-long quest to map the solar system and to map our nearby neighbors really appealed to me. The crowdsourcing part was actually not something that was originally my idea. I got involved because I was approached in terms of co-founding Backyard Worlds, mainly because of the fact that I had been open sourcing my all-sky maps that I had been making with this WISE NASA telescope data. And so the connection there was really like the open data aspect. and the idea of sharing data that you make with others, including originally the astronomical research community, but then eventually much more broadly. One other thing that I really like about this brown dwarf research area is that it has a great adjacency to the field of exoplanets. So, everyone wants to know, are we alone? Are there aliens out there? Is there water in the atmosphere of Earth-like planets? And these are really, really hard questions to ask that we're going to need to make progress on gradually over long periods of time. But brown dwarfs, what's nice about them is that you can actually very readily detect molecules like water and methane in their atmosphere, and so they're a great laboratory to, by analogy, study exoplanets and build up our understanding of exoplanets using brown dwarfs by proxy.
All right, great. So you mentioned this already, but so, you co-founded Backyard Worlds, and I sort of love this idea of democratizing science in that fashion. And it's also not just access, but also agency, because you also, if I understood this correctly, publish, right? Depending on, with sort of citizen scientists. But I have to ask you, in this age of generative AI and LLM, what is it that human beings with their insight, what is the valuable skill that they're still bringing to your projects beyond sort of the machine learning?
Yeah, that's a really good question, a really fair question to ask at this point. I would still say it's definitely the human element of creativity that by far is the most valuable, because the computer algorithms, including machine learning or LLMs, AI, they're really good at doing exactly what they're told or reproducing things that are very similar to what's been in their training data. So if you have a science project where you just want to look for more of the same things that you've always known about and just discover some number more of them, you can probably get somewhere with that with just using machine learning or AI. But then we've seen time and time again in astronomy and other fields of science that the most interesting breakthroughs, the most important breakthroughs, they come from these sort of unknown type of discoveries, where examples I cited in the presentation were Hani's Forewarp or Tabby's star or the accident from Backyard Worlds. And so when you're looking for something that you don't even know what it is, I think the human element of curiosity and creativity really shines there. There's also this notion of avoiding expert bias, which is that we learn so much from our thesis advisors in academia that we have a tendency to repeat the patterns of exactly what was done before us. And if you have someone coming in from a totally different field of engineering or science and looking at the same data but in a very different lens, they have perhaps a better ability to make these rare, unusual, unexpected discoveries. There's also just another aspect, sort of coming back to the human aspect as well, that we get to know the people who participate in the project, and they have other skills and interests besides just staring at the telescope data, right? And so these interests can range all over the place, but for example, many of our volunteers are also artistically inclined, and so we try to use whatever resources we have to promote their interests or to make use of their interests. For example, we've had many press releases announcing Backyard Worlds discoveries through NASA and other outlets where we've had the volunteers, maybe even the volunteers who made the discoveries, do the artwork and the graphics for the press releases. So people bring a lot of different things to the project beyond just making discoveries and staring at the data.
It's good to know that humans are not obsolete at this point, at least. Just in the hope that you've sort of inspired others to sort of start these participatory science projects, what would be some tips that you might have for sort of the ensuring that AI and humans sort of continue to work in a complementary fashion?
Yeah, there's a couple sort of concrete lessons that I think we've learned. The first is that there are different ways to present the complementarity of the AI, the machine learning, with the volunteers, to the volunteers themselves. And so there are a couple of approaches that we sort of learned don't work well. So for example, one approach that should be avoided and doesn't work well is the idea of like presenting it as a test or a competition versus the AI, of like, hey, take this test for us and see if you're smarter than a bot. Like, that's not the right way to frame the project. Another framing that I think should be avoided is one should avoid framing the project as if you just need to collect enough training data from the human volunteers to, as quickly as possible, replace them with the bots, right? So you shouldn't portray it as like, oh, we just need 10,000 classifications and then we can go on from there with the bots and never see you again. So I think there's definitely some pitfalls to be avoided. And then as far as democratizing science, Yeah, I mean, for example, I never owned a backyard telescope. I still have never owned a telescope of my own to this day. Like, that's a big barrier to entry, in my opinion, to participating in astronomy or participating in astronomy research. And so now we have the benefit in astronomy, certainly, of data sets like that's coming from Rubin Observatory or the data set from WISE. And I'm sure this is happening in other sciences as well, maybe Earth monitoring data sets, for example, where there's so much data that literally everyone can look at it, and yet still every single person who looks at it can see something that's never been seen before. And so I think this presents a really good opportunity to try to democratize science, including astronomy. And I think one thing that's really critical to keep in mind in this vein is the idea of public data versus proprietary data. So in astronomy, the vast majority of our data, certainly telescopes like WISE and Rubin Observatory, ultimately, most of the funding from that, or all of the funding from that, derives from the public, from taxpayer money. And so we should feel a strong obligation to be committed to open data to the greatest extent possible, avoiding proprietary data to the greatest extent possible, because it's just not right, fundamentally, to try to sort of hoard this data that was funded by the taxpayers, but also having the data be open is part of what made Backyard Worlds possible in the first place.
Okay, great. So let me just go down some of the questions that have come in on Slido. So if red dwarfs are 300 to 500 degrees Kelvin, are they warm enough to have internal convection even on a geological time scale?
Just a little clarification here. So the red dwarfs are, I would say a few thousand Kelvin. Okay. Brown dwarfs and red dwarfs, yes, they can have convection is the short answer. You don't actually really see that so much in terms of the time series of data of these objects. Like, for example, especially brown dwarfs, if you were to monitor them very sensitively over time with a telescope like the Spitzer Space Telescope or James Webb Space Telescope, what you would see is like very subtle periodic modulations in the signal. And that's because brown dwarfs, if we think they just look essentially similar to Jupiter, right, where they have these bands of clouds. And so you can actually see them rotating around on periods of, say, a few hours or, say, up to 10 hours or something like that.
Okay, another specific question. Do you think we will find a star closer than Proxima Centauri? And if we do, what is going to be the significance of that?
Yeah, this is definitely a question that has interested me for a long time. So just for anyone who doesn't know, Proxima Centauri is the closest known star to the sun. The star system that it lives in, Alpha Centauri, has been known for centuries because the stars in it are so bright you could see them in aggregate by eye with the unaided human eye. And so that is, a few light years away, basically. And so there's always been this question in astronomy of, well, how do we really know that's the closest star or brown dwarf to us? And so indeed, the infrared frontier, the brown dwarf frontier, is the new way that we may still have a hope to find something like that. It would need to be a very cold brown dwarf, maybe even approaching Jupiter temperature at this point. So I have to say, after spending 10 years working on this, I'm somewhat less optimistic than I was before. But nevertheless, there have been various claims in the literature in astronomy of, at low significance, this idea that there are vast amounts of these like free-floating planets or very cold brown dwarfs that are lurking, like a big sea of them, just below the detection limits of what we are currently able to do. And so if we were able to discover, say, a Jupiter temperature brown dwarf closer than Proxima Centauri, it would really change our view of the Milky Way's populations and the distribution of its inhabitants, because as I discussed with Backyard Worlds, we've already revised the prevalence of brown dwarfs that we know of in the Milky Way by a factor of 1.5 or so to be 4 stars per brown dwarf rather than 6 stars per brown dwarf. And so we really need to rethink, well, how many of these very cold, very low mass objects are floating around there in interstellar space. And I think it would also just be a cool illustration if we were to make such a discovery of like how much we still don't know about the universe. The fact that you could, after all of this modern telescope data, still be discovering something so nearby that no one had noticed before.
Okay, great. Getting to near the end, but let me ask a couple of other questions that have come in. So do the volunteers go through any kind of training, and what kind of equipment do participants use in the Backyard Worlds various projects?
The training really consists of like a set of online materials that we've placed within the Zooniverse platform. So there's like a zooniverse.org/such and such URL that hosts the Backyard World's Planet 9 project. There's a landing page there. There's also sort of a page that explains the research objectives. There's an FAQ page that we hope covers some of the frequently asked questions that folks may have. Then there's also a tutorial that walks everyone through the task of actually inspecting one of these image blinks. And there's also a field guide that we call it, where we sort of have a bunch of different examples that show some of the edge cases you might encounter, like here's what a brown dwarf looks like, but here's what an artifact from a bright star might look like as well. So most of the training happens through those online mechanisms, but then another aspect is the sort of more detailed mentorship we're able to do through these online weekly science hangouts with the volunteers, the so-called super users or advanced users.
And you also have places to sort of put input, right? And then get feedback on what the volunteers are sort of submitting.
Right, yeah.
In this whole scheme of things. Okay, great. So one more question. Even though you're searching for a planet in our own solar system, you and others have found brown dwarfs in other solar systems, is the question.
Yeah, that's definitely right. And we found them in a range of different configurations. So the examples I showed in the presentation were what we call wide binaries, where historically these have actually been called visual binaries, even though in this case you're seeing in the infrared, which isn't really how your eyes see. But these so-called visual or wide binaries, the separations are, say, thousands of astronomical units or tens of thousands of astronomical units, and you can literally see the two objects, one being a brown dwarf and the other solar system, moving across the sky together as two separate points of light. But there are other configurations where you can have the brown dwarf much closer in, and so sometimes you can actually even detect, similar to how we detect so-called transiting exoplanets, where the small planet blocks a tiny bit of the light in front of the star as it passes in front of it. You can have the same effect with brown dwarfs in other solar systems, where they are transiting in front of their host star, and so we know about them that way instead.
Okay, great. So let me ask sort of a big question now. So what do you think are some of the big open research questions in astronomy today, and what is your advice for young people who want to be astronomers, study physics and astrophysics in particular?
Yeah, so I think one of the big questions we've touched on a fair amount already here, which is the are we alone question, which involves this idea of exoplanets, planets around other stars, and brown dwarfs can also help us learn a lot about this same topic just because they're so adjacent in terms of their mass and temperature and atmospheres. There's also, zooming much more out from the local neighborhood of the sun, there's these bigger ideas of dark matter and dark energy, which are thought to make up about 95% of the energy content of the universe, and yet we have no idea what they are in detail. So I would definitely say those are two of the premier open mysteries in physics and astronomy. I think the advice I would have is, when I was in high school, say, the Zooniverse didn't exist. And so I do think that if these tools had been available so readily online when I was younger, I may have been exposed and gotten the chance to participate earlier. And so I would definitely encourage folks interested to sort of get a little bit of a taste of it through participatory science, whether it be astronomy or in other fields of these online projects. And then more generally, as far as what to do career-wise, the world is changing so fast with technology and industry and society. It's hard to know what things are going to look like even a couple years from now, let alone 10 or 20 years from now. But I think the key is to really be curious and adaptable, because I don't think we know exactly what tools we're going to use to do astronomy research in, say, a few years or 10 years from now. But just the curiosity and willingness to adapt and learn and still want to answer these big questions about the universe is what's going to drive you forward to be able to make your way through.
Great. Thank you, Aaron, for your interesting presentation and perspectives. I also want to thank our audience for their terrific questions. You can find out more about future programming and watch videos of past events at radcliffe.harvard.edu. Thank you for joining us today, and have a good rest of the day.